database. And so what we're going to be doing is we're going to run code that's going to hit the Twitter API, much like we did in a previous chapter, and we're going to retrieve the data, but we're going to remember the data so we don't have to retrieve it again. Okay, and so we're going to keep track of people's friends, and what we're doing here is sort of illicitly pulling down, slowly but surely, based subject to our rate limit, we're pulling down who our friends are. And so let's take a look. We're going to use URL-lib and URL-lib error, Twitter URL, which was code that augments my URL to do all the OAuth calculation. We're going to get JSON data back. We're going to make a database, and we have to import SQL because of the way Python doesn't trust any certificates, no matter how good they are. So this is our URL to talk to the Twitter API. We're going to make a database, and again, the way SQLite works is if this spider.sqlite doesn't exist, it creates it. And we get ourselves a cursor, and we're going to do a create table. This, if not, exists. Some SQLs, but SQLite 3 does this. Create table if it doesn't exist. We want to start this over and over. Unlike the tracks example, I want to start this over and over and not lose data. And this is a spidering process, and we'll see a lot of these where we want a restartable process where we use a database. So if we're starting with nothing and there's no file, a Spider SQLite, it creates this table, and it's the name of the person, whether we retrieved it or not, and how many friends this person has that we know of in our database. Now this little bit is to deal with the SSL certificate errors. The certificates are totally fine, but Python doesn't trust any certificates by default, which is frustrating, but whatever. So here we're going to have a loop. We're going to ask for a Twitter account. We have to type quit to quit. If we hit enter in this case, we're going to actually read from the database an unretrieved Twitter person and then grab all that person's friends. Okay, and so then we're going to do a fetch one, get one, and that's going to get the name of the first person, the sub-zero. If we had more things than name here, sub-zero is the first of those. Fetch one means get one row from the database, and sub-zero means the first column of that first row. And if this fails, then we've retrieved all the Twitter accounts. And so, you know, we're going to augment this Twitter URL using this makes, you can look at the twurl.py code. This basically requires the hidden.py file, which has your keys and secrets in it. You got to get hidden.py updated. I've got it updated, but I'm not going to show you because it has my keys and secrets in it. And so we're only going to take the first 5, which means we're probably not going to find friends of friends of friends. It's only the most 5 recent ones. We could run this with a much higher number to get to so we have more than one friend. We'll show the URL while we retrieve it. We will do our URL open, we'll do a read, and then we'll do a decode to make sure that this this will give us data in UTF-8, and then decode will give us data in Unicode, which is what we need inside of Python. We will ask for the headers from the connection. We'll say, give me the headers, give me a dictionary of the headers, and the X rate limiting header from the Twitter API tells us when we're going to be told we can't use this API anymore, because this is one of those things. And then we're going to parse and load the data that we got from Twitter and get a I think it's a list. Yeah, it's a list. And then we could dump this if you want. In yours, you can undo that. And then what we're going to do is we've just retrieved this person's screen name and their friends. And so the first thing we want to do is update the database and change the retrieve from 0 to 1. And that's because we're going to use this to know about unretrieved. So retrieved being 1 means we've already retrieved it, and we did retrieve it. So for that account, we've retrieved it. And then what we're going to do is we're going to parse that. And so this is similar to the Twitter code we did previously in the Web Services chapter. We're going to go through all the users. We're going to find their screen name. We're going to print the screen name out. Okay, and then what we're going to do is see if, let's see. So we're going through all the users who are the friends of this person, and we're going to say, oh, okay, let's select the friends from Twitter where the name is the friend person. And what we're going to do is we're going to do a cur fetch one of this Twitter the name of the friends. This is the friends screen name, right? So we're going to say, oh, okay, if we get this, we're going to get that friend screen name, and we're going to get how many friends this particular screen name has. If we find a URL, we find it in there, we're going to do an update statement and add 1 to their friend count, how many friends they have, and then keep track. This count here is not in the database, it's just so I can print it out at the end. If there is no record for this particular friend, we're going to insert them into it new, and we're going to say, here's the new person that we just saw. Here, that's their name. We're going to set retrieve to 0, and we're going to say that they have 1 friend. Okay? And then we're going to commit the transaction, and then we're going to close this at the end. Okay? So let's go ahead and run this. The first time it's going to create an empty database. So I'm going to say Python 3 TW-Spider. So ls star SQLite. Nothing there. Python 3. Oops, that's because I removed it. Python 3 TW-Spider.py. Okay, so I'm going to start with a Twitter account, Dr. Chuck. And so it's doing this retrieval, and don't worry, showing the token and the signature is not dangerous because you don't have the keys or the token, I mean the secrets and the token secrets, so don't get all too worried. So I have 11 calls left, so I hope this all works. One of my friends is Stephanie Teasley, and these are in reverse order, so let's grab Stephanie and ask for Stephanie's friends. So now we just retrieve Stephanie's friends, and here are Stephanie's most recent friends. And then I can just hit enter and it'll randomly pick. Let's see if I can in the database. Let's open this up, file open database. Hope I don't lock myself. Sometimes it's a little scary when you look at the database and you're just checking. So this is what my database looks like. We retrieved Stephanie, and this is how many people. So these are the friends of Stephanie and me, and these are how many. I'm not in there. So we've retrieved Stephanie, which was a friend. So let's go grab I don't know. Let's grab Tim McKay and get that one. Remaining 10. I don't have too many of these. Tim McKay, right? So there we go. Remaining 9. And so if I do a refresh on this, then you see I've got some more folks. If I hit enter here, it will retrieve, it'll pick one randomly based on the retrieve being 0. So it won't pick Stephanie or Tim because they're 0, but we have lots of other folks to pick randomly. And we'll hit enter. So it picked, who did it pick? It picked screen name Live EDU TV, which is ironic because I'm recording this on Live EDU TV right now. And so we can keep hitting refresh, and away we go. So I'm going to stop now because I only have 8 remaining, and so I'm going to type quit, and so we will see we'll see how that works. So that's how it works. Now remember that you've got to edit the hidden.py file to make this work because we are talking to the Twitter API. If you don't edit that file, it won't work for you. Okay, so I hope you find this useful. Cheers. So now we're going to take a look at how we deal with more than one table, multiple tables, because the real power of SQL and the power of database performance has to do with when you start connecting tables together. If you go back to that original mathematics, it models data at the intersections between the row and the columns. And these intersections are the magical bits. And so breaking an application to use multiple tables is an art form. It takes a while. There are some simple basic things that you can learn, and we'll teach you here. And so it's not too hard to learn the basics, but then it's much more complex to be super skilled at it. And in general, advanced databases, in my mind, it's hard to teach advanced databases because they're always so contextually grounded. Something like a Twitter or Google, the databases are so specialized. By the time you make everyone can do small to medium-sized databases using the basic techniques, but at some point, once you escape medium-sized databases, you end up in these sort of narrow things and optimize each database very separately. And so I just tell people, learn the basics really, really well, write programs, and then go do real work. But database design is the act of figuring out the data that your application is going to want to store and spreading that across multiple tables. But we don't just do it randomly, we do it very much cleverly. And if you look at a data model, this is what it looks like. And what we're showing here in this data model is we are showing 5 tables. And this is a kind of a calendar kind of a system. And we're seeing the columns that are in each of the tables, and then we're seeing the relationships between the tables. And even in these relationships, there's kind of a little bit of code. And when you have an arrow that looks like that, there's many of those to one, and this is a many-to-one relationship. Many-to-one relationship. We'll talk all about that stuff. But if you go into an organization and you have a really large and complex data application, they might have something printed out on the wall that looks about like this, which shows the database tables and connections, et cetera, et cetera. And they might say, oh, your job is to go down in this little corner, add one field there, and then do this, and then connect it with this thing over there, and then make a screen that shows all these things that pulls from this table, this table, this table, and that table. And that's your job if you're a programmer on a large software development project. These database models become sort of like the core backbone of the knowledge that applications are managing and using. So the idea is that you take your application. We're going to start really simple. We're going to take your application and you have to draw a picture. And the basic rule, and literally you could spend course upon course learning about database normalization. But I'm going to distill it into one basic rule, and that is never put the same string data in twice. So my name, Charles Severance. If I build a database well, you should go into that database and you'd say, okay, the words Charles Severance, which is the name of a person, me, in that database, only shows up once. And what we do instead is we connect things together and model my name as a connection to the record that has my actual name in it, rather than putting my name all these other places. And so the idea is to pull duplicate data out and make only one copy of it. So there is the users, and in there is the user's name, and the username shows up only here, and everything else points to the particular user entry. So that's the idea. And so here is our first application. We are working as a startup. We just quit all of our jobs, and we are going to build a music management application. I mean, what a great idea. Don't you think that'll be quite successful? And so we have mocked up and we have figured out that this is what our music management application. We want to track people's tracks, know something about what artists and albums and genre they are, and we want to have ratings and how many times we played them and how long they are. Well, that's the data that our application needs to represent. And we've done testing on this and wireframes, and everyone loves this, a great user interface. And so this is how it's got to look. But we're going to have billions and billions of tracks in these things, and so we want to come up with an efficient database to handle this. And so we're going to take a look at this and look at each of the columns, and we're going to ask ourselves, is this column part of one of our existing objects, our existing tables, or is this object have to create a new table? And then once we've defined those different objects, we connect the tables together and model the connections. Now, a little trick to kind of make it a little easier on ourselves is we can look in these columns and look in the columns that have duplicate information vertically, that's string information. So a rating is just a number like 0 through 5. So we don't worry too much about integers and numbers and that kind of stuff or whatever, but we do look for strings. And the problem here is we got like these strings occur many times. And so these are the problems. And so we have to put these things where there is replication of string data kind of in the vertical dimension. We have to put those in different tables. And so we'll start out. Now the first question that you have to ask yourself when you're going to draw this picture of how this data is in multiple tables and connected together is, what is the first one that you're going to write down? And this is an interesting debate, and often people are sitting in a conference room, and people who have experience kind of know what to do. Usually if it's a multi-user system, like a learning management system, the users might be the central concept. Perhaps the courses might be the central concept. This is a single user system, and so you can think, well, what is really this application about? It's not about people, it's one person, but it is about tracks. And so we can say, okay, here we'll take the track is probably the sort of most foundational notion of this application. And then we can take and say, okay, now that we've decided that tracks are the foundational notion, which of these columns are simply an attribute of the track? Not really, and the cheating way and the easy way in this particular one is like these numbers, all these numbers, like this number and these numbers, not that one. They just go along with track. And so we'll put that in. We got the track title, rating, length, and count, and we put that in. And then the question is, we've got the remaining things are, we've got the artist, we've got the album, and we've got the genre. And so we can say, okay, well, we've got some vertical duplication, so we're going to say, okay, this track probably belongs to an album. So let's pull out the album into its own table. Oops. Pull the album out into its own table. And so pull the album out into its own table. And so that pulls that out, and then you say, okay, what would be the next thing that we're going to pull out? So we pulled out the track, we've got this taken care of, this taken care of, that taken, now we've got the album. Well, albums belong to artists, so let's take out the artist. And then we'll pick where the genre belongs, and we'll just say that the genre belongs to the track. And so, because there might be albums with more than one different genre. So each album is not necessarily a rock album, it could have a rock track and a country track, etc., etc., etc. And so now what we've got is we've got 4 tables, right? We've got a track table, we've got an album table, an artist table, and a genre table. And if we sort of double check, all of the columns that had vertical duplication in them now have their own little table. So we can eliminate, the next thing we'll do is to show how we're going to eliminate this vertical data replication by showing how you represent these relationships that we just created inside of the database. Now we're going to represent these relationships in the database. And again, what we're trying to solve here is this notion of database normalization, third normal form. There is so much theory, right? But in this lecture, I'm just going to condense this down to don't replicate string data and use what are called keys. Use integer keys to point at those things. And we're going to use these integers then to point. So we'll assign each row an integer, and then we're going to point from one row to another using those integers. And so we're going to add these special key columns to each of the tables, and help in the database will even give us help managing those. Now, and so we still need to keep track of, you know, who is the creator of the album, which album a track belongs to. We've got to create these relationships, and we have to come up with ways to store those relationships. And so the idea is we're going to have a column in a table, which is the key column, and we're going to call this the ID column. And so this is a row. It might have many bits of data here, but in this case it's just the name of an artist. So this album is going to belong to an artist. And we're going to assign a number inside the database, and so that Led Zeppelin is 1 and AC/DC is 2. And so we have this key, this is called a primary key, and then later when we want to say that the Who Made Who album really was done by AC/DC, we put the number 2 in. And so the difference here is, instead of saying AC/DC, in this record, we just put the number 2 once we've established this number. So we assign keys, and then we have these pointers that point back. And so that's how we model a relationship with these small integer numbers. And so there are 3 basic kind of keys that we use. One is the primary key, and that is that little ID column that is just a number. But once we give Led Zeppelin the number 1, Led Zeppelin is the number, has got the key 1 for the rest of that database. The logical key is the text area that we use that you might look up. So the title of the band or the title of the album, that's the logical key. And then the foreign key is one of these keys that is really pointing to the primary key of another row. So that's called a foreign key. And you might think that you want to use something like an email address as the primary key for a user table or something like that. The logical key should always be separate, and there should always be a primary key, that integer number. Because things like logical keys do change. People do get new email addresses, and if you've got that email address as a foreign key pointing all over the place, it doesn't work out so well. And so that's why you use these small integer numbers that have no meaning outside. So sometimes if you're on a system and you see a URL and you see some number like 422,016, you're like, oh, that turns out to probably be my primary key in their database. So sometimes you can look in a URL and you can see these primary keys in the URL, but they don't mean anything outside of that particular system. So like I said, a foreign key is a key that is really pointing at a row in a different table. And so we have the album has a primary key for it, but the artist underscore ID points to a row in the artist table, as we will soon see. I have a naming convention, and in my naming convention on this lecture I use ID for the primary key, and then artist underscore ID I use uppercase for the table names, and then artist underscore ID says this is a key, this is just a key that points to the ID key of the artist table. And so that's what I do. So you'll see in all my stuff I'll use that. It's a convention. It's not something SQL forces you to do, but you will find when you go to organizations and work on their databases, these conventions are very important so I can do something and you can understand the rules in which I created it. Some of these, you'll find this used by some people, you'll find completely different conventions, and that'll be okay. Whatever convention your organization uses, learn that convention. So now we're going to talk about how we put these keys in and then how we actually make the connections from one row to another row. So now that we know what a primary key, logical key, and foreign key are, we're going to actually start putting these together and creating tables that have these kind of values in them. So when we were done, we drew this picture that was sort of a logical model of how our data would be spread across 4 tables and how those tables are connected. Now we have to take this and we have to map it in a way that leads to the columns and the needed columns in each of our database tables. And so here's what we do. We basically have to take, and for each of these, when we're going to build a track table, we add a primary key. So we just added an ID field to every one of these things, and that's so we have a place to store the sequence number of this particular row. We have logical keys, we've just marked those are strings, and then we have things like, rating, length, and count, they just kind of go in here. And now we have to model a relationship. So what we do is in the table that the relationship starts from, we put one more column in, and this is the one I will name album ID, and that just is an integer column that's going to record the album ID. So this might be 16, and then 16 goes in here. So there's one of these columns that's a foreign key that points to this, and that's why it's foreign. This is a key that's not in the track table. This is a key in the album table that we're pointing to, and so there's a foreign key. And that's what we have to do, and we just do that over and over and over again, and we quickly convert that picture that was a logical picture to having every table has a primary key, and every time we have a starting point, we have a foreign key, and then foreign key. And then we mark these things as logical key, logical key, logical key, and we'll see how we do that. And so that's the picture. Now we have a picture of exactly how we're going to lay these tables out and the fields that we need in these tables. So we're going to do a create table statement. And I've got this create table statement sitting there. And so this one's going to be a little bit different. We're going to say create table artist, and the ID field is integer, and we're going to add all of this stuff. This is adding to the column to tell it additional stuff. It's a primary key, which means we're going to use it to look up a lot. It's automatically incremented, which means the database is actually going to provide this number for us as we insert records. It's not allowed to be null, it's not allowed to be empty, and it's supposed to be unique. And then it's going to have, the artist is going to have a name column that's just text. So let's do that. We already have our users, and now we're going to do a create table in this SQL, and you can do that. That's okay, that's totally fine. And we have to get this right, and we say away we go. And so now if I take a look at database structure, I've got a users table as well as that users table we were playing with before, and this artist table. Let me go ahead and delete this users table just to say goodbye. Okay, so now we have the artist table, and we take a look, and it's got an ID, and it knows all about this stuff. Okay, so that created the table. We're going to keep doing this. The next thing that we're going to show here is we're going to show the foreign key, right? So artist ID is just an integer. In some database languages like MySQL and Oracle, you would put more stuff here to say this is a foreign key, blah, blah, blah. But in SQLite, we keep it simple and just say that is an integer column, that's a foreign key. The album table has a primary key and a foreign key, and then the title. So we'll go back and we'll grab that text out of my little page, this create table, go back to execute SQL, and then run that. And we'll continue. The genre table has an ID on it, and primary key order. You'll just copy and paste these. That whole thing, you do that over and over and over again. So we'll go in here and run that one. And so the last one we're going to do is the track table. And the only thing that's kind of weird about the track table is it's got two foreign keys, right? It's got an album ID and a genre ID. Once you draw the picture, you just sort of literally translate these things. It's got two foreign keys and a primary key that's pretty much just like all those other primary keys. And, you know, integer counts an integer and length is an integer, all that stuff. And now we've got it. So if we take a look at our database structure, we're going to see that our album, genre, and track are all set up. And these are no columns that we just made with those create statements. Okay? So now let's insert some data. This first insert statement is kind of important to take a look at. So insert into, by the way, the keywords can be upper or lowercase, table name, columns. Now, this table has two columns. It has ID and name, but we told the database that ID was auto increment, so it's going to actually give us the number. It's going to assign the number rather than make us assign. We could make it be 1, 2, 3, but we say, hey, database, you're good at this. Why don't you make it 1, 2, 3? And so there is going to be a record that it adds Led Zeppelin. So let's take a look at that. So we'll insert Led Zeppelin. Oops. Over to SQL, insert Led Zeppelin and run it. So now if I look at database structure and I look at let's look at browse data and look at the artist database, you will see that I put Led Zeppelin in, but this ID field here was auto incremented. And so it was put there by the database. And now when we do the next insert, which is AC/DC, and we take a look at the data, we'll see that AC/DC is 2. Now, if you're writing this in a program, if you're going to write this in a program, you can get these numbers back from the database in your program, but I'm not writing this in a program, so I have to remember that 1 is Zeppelin and 2 is AC/DC. So I'm going to keep myself a little cheat sheet here to remember that. Because everywhere else in the program that we want to say Led Zeppelin, I got to say 1 now, because the artist ID of 1 means Led Zeppelin in those rows. And so now we're going to go back and we're going to take a look at the next one. And now we're going to put the genre in. If you think about it, we're working from the leaves out, where the track will be the last table that will update, because we have to define the keys for things like rock and metal and Led Zeppelin and all those other things. And again, even though the genre table has 2 columns, ID and name, we're only going to specify the name and let the database assign the value. So I'm going to insert both of these and use the semicolon trick. Put a semicolon here and a semicolon there. And run that. And so if I take a look at my browse data and I look at the genre, it's assigned 1 to rock and 2 to metal. And I'm going to write that down. 1 rock, 2 metal. I should have done something like rock and country because I can't even tell the difference between rock and metal, but whatever. That's my musical skill is not what's at issue in this class. So now we're going to put an album in. The album is the first thing that has a foreign key. So if you remember the thing, the album points to artist. And so that means it has a foreign key of artist ID. And so we have to explicitly say this because the system doesn't know which artist Who Made Who is, but we know that Who Made Who is AC/DC, and that's 2. And so we know to put artist ID in, so we'll say insert into album, title, artist ID, and so we have to know what this 2 number is. And of course, because we have our handy little cheat sheet, we can go over to execute and run that. And I'll put a semicolon there and a semicolon there and run it. And so now we have in the album field, we now have this. And so this was assigned, and so Who Made Who, I still have to write down that Who Made Who is album 1, and album 2 is Led Zeppelin 4. That makes it even more complex because the name of the album is Roman numeral 4. I'm sure I can figure that out. Okay, so the next thing that we're going to do is we're going to insert the track record. Now if you think about the track record, the track has 2 foreign keys, and it's got a lot of stuff. It's got the title, it's got the rating, length, count, but then we got the 2 foreign keys. And so we have to know these numbers. So this 2-1, this 2-1, this 1-2 is the genre. We're specifying the genre and the album that this track is from by those numbers. Now, again, we have to use this cheat sheet, but if this was a program, the program would know that 1 was Zeppelin and or 1 was Who Made Who and 2 was Led Zeppelin 4. And so that the programs, this kind of stuff is easier for the program to understand than for us to keep track of and understand. But just so we can get through these few records, and that's why I rely so heavily on my cheat sheet. So here we are with all these numbers. The foreign keys are the tricky part here. Everything else is really quite straightforward. So now I'm going to insert 4 records into my track table. And then run that. Okay, so if I browse data and I look at my track table, this column here, this ID, that's the primary key of the track table, and then here are the 2 foreign keys. Now the interesting thing is now there is replication in these columns, but the numbers are what's being replicated, and that's okay. We went a long time just not to put Led Zeppelin 4 in twice. We could have made this a string, but by making this an integer, it saves tons of storage and makes it super fast. That turns out to be one of the key things that makes databases super fast, is using these integers. So we take a look at all this stuff. We see that in a sense, by using these little numbers, we are pointing to rows in other tables. The foreign keys are always pointing. They always point to their ID. So these foreign keys are out here. This is the primary key up here. And they always point to a row in another table. And so we have modeled all those relationships. And you will notice that in this entire database, the Who Made Who only appears once. The word rock only appears once. The word AC/DC only appears once. What we have is we have duplication in our data, but we are duplicating the relationships, i.e. these little integer numbers, not duplicating the data itself. And in something that's this small, it seems irrelevant. But if you have billions of records or hundreds of millions of records, it's very relevant. Very, very relevant. So the next thing we're going to do is take a look at how you actually reconnect all this stuff together once we've sort of blown it out in these, using these foreign keys and hand constructing all these relationships, now how we bring it back together to show the data to the user. So now that we've carefully constructed our relationships in the tables, we need to reconstruct the data to show our users. And you can kind of see how you would go pull this stuff together, but there's a wonderful capability in relational databases called join that brings this all back together. And so we have done this for efficiency of storage, efficiency of scanning, etc. But we do need to traverse these foreign keys at times, and the database software will do this for us automatically. So the join operation basically is a way to specify in a select statement that you want to pull data out of more than one table, and then specifying using what's called the on clause exactly how you want that data pulled out. And so here we go. We already have a table, an album table to the artist table, and the foreign key, and we want to, in effect, pull data from both the album and the artist, the album title and the artist name, and we want to show that. And so we're going to say select, which is the same select statement. Here's a little different syntax. This is the list of fields. This is table.field, so it's the album title and the artist dot name, comma there, from the album. And I always start with where the little arrow starts from, album joined with. So that is going to walk down this connection from album to artist, album joined with artist, don't say with, I just say it, on, and then this is the conditions upon which that join is going to happen. When the album's artist ID, which is this column here, album's artist ID matches, think of that as is equal to or matches the artist's ID. And so it only connects the rows here when there is a match between these two tables. And so if we look at this and we see that you know, this one matches this one and this one matches that one, and so it's the join connects conditionally, and it connects when the on clause is satisfied. And so when this whole join runs, this is what we get. So you select all this stuff. Now this is an abstraction. Are you writing a loop? Are you doing two nested loops? How are you exactly bringing all this data together? We don't care about that, because that's the beauty of SQL. That's the beauty of how we do this in a database. So now if we can just run this command. So let's grab this command. Select track title, genre name from track, join genre, that exact query. Case of keywords doesn't matter. And we go over here and we run this as SQL. And we run it. We get, oops, I got too far. Let's do this one. So let's do that one there. Select artist name. I have to add that one to my little cheat sheet. The next time you see the cheat sheet, it'll be right. So the title, so this is coming from one table and that's coming from another table. Okay? And so that's one. So here is something we can do that gives us a little more detail on that. We can say, so this is where the connection, and so you can think of the join as sort of spreading one table and connecting it to the other table. And so what we're going to show here is it's exactly the same. The only thing we're going to do is we're going to add these two columns so you can see where the match happens. And so this is one table, this is another table, and these are the kind of columns in common, even though they're not. They're the columns that match. This is where the on clause is happening, right? We have taken this table joined with this table on these two things connecting with each other. So you can almost, in some language, some variants of SQL, this would even be a where clause. So you connect these two rows, but only connect them when those two numbers match. So you can see, I mean, if we run this, I'll just run this. And again, you just see this is where it connects, okay? Now, interestingly, we can see what happens and what the purpose of the on clause is if we omit it. So this is exactly the same as that previous query, except there's no on clause. So it's select all four of those fields from the track joined with the genre. So it's basically taken the track table and the genre with a join, but no on clause. So it's not filtering for matches. This is a match, this is a match, that's a match, that's a match. But we don't have an on clause, so the matchness doesn't matter. And so you're going to get all possible combinations. And literally, if there were, 10 on one side and 30 on the other side, you would get 300 rows in that join. So it'd be all combinations, except the on clause reduces the combinations. And you might think, whoa, this is really inefficient. And I will say that's what my first reaction was when I first saw this, but it's not inefficient. That's the beauty of abstraction. That's the beauty of SQL. You say do it, and it just figures that out. So Let me grab this and you will see that we can run this one as well, and that kind of gives you why the on clause is important, because now we have a whole bunch of these things, and the on clause just filters that out. So if we would just add the on clause back in, then that would only show the ones we showed on the previous slide. So that's why the on clause is important. The join is like all possible combinations of all pairs of rows between these two tables. On is, oh, but only where these two things match. Now you might think that it's inefficient, but the on clause turns out to be the way it becomes efficient. Okay. So now we're going to do the same thing where we're just going to take the track title and the genre and going to connect that together. So we select this. We need to join from one table, join to the genre table with an on clause. And so we're going to make those connections. And the only thing we're going to look at is the title and the genre name. Oh, oops. And then run that. And so we got the title and genre name. Now the thing you'll notice is for the first time, we now have replication of string data in a vertical dimension. That's okay, because the data is not replicated in the database. The data is now replicated as a result of the join. And so we are going to reconstruct what the user wants to see, which the user originally, all the way back to the beginning, wanted to see the duplicate information in the vertical axis. But now we're reconstructing it. We didn't waste the space or performance in our database, but we still have to show them. And so now the next thing we're going to do is a monster. We are going to reconstruct across all four tables. And you might think this is really hard, and sure, it's going to be a little tricky, but as long as you follow the naming convention and the naming convention makes sense, we're going to do a select from the track's title, the artist's name, the album's title, and the genre name. From the track, join genre, join the album, joined artist. And so the joins follow the little arrows, right? And then the on clause qualifies each of those arrows, when to follow the arrow. And then this becomes pretty easy. It's a foreign key. The track's genre ID, that's a foreign key, equals genre.id. That's primary key, that's a foreign key because I name it that way, and I know that this goes to that genre table because I name it that way. And track's album ID is equal to the album's ID, foreign key, primary key, and album's artist ID is equal to artist's ID. After a while, you can type these pretty fast as long as you follow a naming convention and you know the naming convention. So this looks like it's really hard to do, but after a while, it's really just a pattern. So let's go ahead and run that one. And it will, assuming we've done everything right, replicate all the data. So there's all kinds of vertical data now being replicated. Every column has vertical data. Again, it's not in the database. The select and the join are reconstructing vertical data as it needs to be shown to the user. And so, if you've been following along, probably a couple hours later now, we started with a picture that was our mock-up of what we wanted our user interface to look like, and it had vertical stuff, and we're like, oh, we can't put that in a database model. And then we carefully built a database model that didn't have the data, and then we're like, we got to reconstruct it. So we used join to reconstruct it. And so after all that, we went here with a clean little model with 4 tables all beautifully connected together, and then we had to join it all back together. So join reconstructs it. And again, the key is the storage is efficient, the scanning is efficient, and we still use the join to produce the output that we ultimately want with all the sort of vertical vertical replication that our users really want to see. So there's one more kind of relationship. That was called a one-to-many relationship. That was actually 3 one-to-many relationships, and the other major relationship is what's called a many-to-many relationship. We're going to do some code walkthroughs, actually running some code. And if you want to follow along with the code, the sample code is here in the materials of my Python for Everybody website, so you can take a look at that. So the code we're going to look at is from the database chapter, And we're going to look at tracks.py. So a lot of the lectures that I give in this database chapter are just about SQL. And this is really about SQL and Python. So I'll go through this in some detail. So the code that I'm going through is in Tracks. There's also tracks.zip that you can grab that has these two things. It's got this library.xml file which you can export from your, if you have iTunes, you can export this, or you can just play with My iTunes. And so this is also going to review how to read XML. So we're going to actually pull all this data. And this XML is that Apple produces out of iTunes is a little weird in that it's kind of key values, and so you see key value pairs, and it even uses the word dictionary. And so it's like, I'm going to make a dictionary that has this, then a dictionary within a dictionary. This to me would be so nice if it was JSON, because it's really a list of dictionaries. This is a dictionary, then another dictionary, then another dictionary, and then the key for that dictionary. And it's a weird format, but we'll write some Python to be able to read it. And so you export that from iTunes, and you can use my file or you can use your file. It might be more fun to use your file. So here's tracks.py. We're going to do some XML, and so we import that. We're going to import SQLite 3 because we want to talk to the database. And then we're going to make a database connection, and in this, once we run this, you'll see that that file will exist. And so right now, if I'm in my tracks data, that file doesn't exist. But what we'll see is this is going to actually create it. Now remember that we have a cursor, which is sort of like a file handle. It's really a database handle, as it were. And in order to sort of bootstrap this nicely, we are going, because this code is going to run all the time, it's going to run and read all of library.xml. In later things, we won't wipe out the database every time. And so I'm executing a script which is a series of SQL commands separated by semicolons. So I'm going to throw away the artist table, album table, and track table. Very similar to the stuff we covered in lecture. And then I'm going to do the create table, and I'm doing this all automatically. And you'll notice this is a triple quoted string, so this is just one big long string here, and it happens to know that it's SQL. I'll thank you, Adam, for that. And so it creates all these things. Now, it's not quite as rich as the data model we built because there's no genres in here. And so it's artist, album, track, and then there's a foreign key for album ID and a foreign key for artist ID, which it's sort of a subset of what we're doing. And so when that's done, that actually creates all the tables. And we'll see those in a moment once we run the code. Then it asks for a file name for the XML, right? And so that's what that is. And we're going to, I wrote a function that does a lookup that it's really weird, because if you look at these files, like in this dictionary, there is a key, right? And so the key of this dictionary, this really should have been a key value pair, but so there's this weird thing where the key for an object is inside of the object, and so we're going to grab we're going to loop through all the children in this outer dictionary and find a child tag that has a particular key, and so you'll see how this works. And this was something I was going to use over and over again. And so the first thing we're going to do is we're going to just parse the string, and this is the string, and then this, of course, is an XML ET object. And then we're going to say we're going to do a find all. And so this shows how the find all, we're going to go the third level dictionaries. We want to see all of the tracks. And so we have a dictionary and a dictionary and a dictionary. And so what we want is all of these guys, right? All those guys right there. Right? Track ID. So we're going to get a list of all those. That'll be the first one. This will be the second one, because the find all says go to find the dictionary key, then a dictionary key, a dictionary tag within that, and a dictionary tag. And then we'll tell how many things we got, and then we're going to loop through, and entry is going to iterate through each of these. and see, we'll get our name and our artist. Another one bites the dust, a queen, and away we go. And then the next time through the loop, we'll hit this one. Okay, so then what we're going to do is we're going to go through all those entries, and if there's no track ID, and if that's this track ID field, where are you hiding? Track ID. If we don't have that, we're going to continue. And then we're going to look up the name, artist, album, play count, rating, and total time. Okay. And so here they are, play count. A lot of those things that we had in the sample lecture that I did. And we're going to look those things up, and we're going to do some sanity checking. If we didn't get a name or an artist or an album, we're going to continue. We're going to print them out, and then we are going to remember how you have to get the primary key of a row so you can use it. So the way we're going to do this is we're going to do an insert or ignore. And so this or ignore basically says, because I said that the artist name, go up here, I said the artist name is unique, which means if I try to attempt to insert the same artist twice, it will blow up. Okay, because I put this constraint on that. Except when I say insert or ignore, that basically says, hey, if it's already there, don't insert it again. So what I'm doing here is insert or ignore into artist. So this is putting a new row into the artist table unless there's already a row in that artist table. And this syntax right here, you know, the question mark is sort of the where this artist variable goes, and this is a tuple, but I have to sort of put this comma in to force it to be a tuple. So this is a way you have a one tuple. And then what I need to know is I need to know the primary key of this particular artist row. Now this line may or may not have actually done the insert, and so I need to know what the ID for that particular artist is. So I do a select ID from artist where name equals. Now it either was already there or I'm getting it fresh and brand new. So I do an artist ID equals, I fetch one row, and it's going to be the first thing, given that I only selected ID. And so this artist ID is going to be the ID. Now I have the foreign key for the album title, right? And so now I'm going to insert into the title artist ID. This is the foreign key to the artist table. And I got this value that I just moments ago retrieved. And I got the album title. But this also is insert or ignore, because, and now if you look, I have unique on the album title. Yep, unique's on the album title. So that'll do nothing. It doesn't blow up. Or ignore says don't blow up, just do nothing, because this next line is going to select it. And I grab the album's foreign key for either the existing row or the new row, and then I'm going to insert or replace. And so what this basically says is if the unique constraint would be violated, this turns into an update. Now not all SQLs have this, but SQLite has this that basically says insert or replace. Some SQLs are totally standard. Some things we do, like this select statement is a totally standard part of SQL. Then insert is totally standard, but insert or replace and insert or ignore is not totally standard. But that's okay. It works for SQLite, which is what we're doing. And so we have the title, album ID, length, rating, and count. And then we have a tuple that does all that stuff. And of course, the title is unique, right? The title is unique in the track table as well. And so we've inserted that. So the clever bit here is both dealing with new or existing names in these three lines, and we see that pattern twice here where we're doing that. Okay, so there's not much left to do except run this code. Hopefully it runs. Python 3 tracks.py and library.xml. Whoosh. Okay, so that is my So we found 404 of those dictionaries, 3D dictionaries, and now it's starting to insert them, insert them, insert them, insert them. And we can take a look at, so we can do an ls-l or dir on Windows, we'll see that we made a track database. We extracted the data from this library and we made a track database, and we have all these foreign keys. So let's go and take a look at the SQLite browser. File, open database, TrackDB SQLite, and come on up. Where'd you hide? I got it minimized, so there you go. Let's look at the database structure. We have an album, this is the structure, artist and track, we have no genre, and this is all like we did it by hand, except Python did all this work for us. If we take a look at the data and we start from the outside in, we have the artist names and their primary keys. Right, there's the artist names and primary keys. And then we have the albums, and we have the artist IDs. See the artist IDs, how nice those are. So we have the primary key here and the foreign key there, and then we have the title. And if we get to the track, we have the album ID, and away we go. So if I was clever, I could be able to type some SQL. Oh, great. If I was smart, I'd have had this in a paste buffer. So select track dot title album dot title artist dot name. I think artist has names and albums have titles. Yes. Okay, so I can do that from track join album, album join, let me make that a little bigger, bring that over here, album track join album join artist. Now I need an on clause, and I can say track dot album ID equals album. Notice how I know the name that I named these things, and album dot artist. This is so great when you use a naming convention, artist ID. Golly, I think that might work. So let's just see what we get when we type that into the SQL box here. Execute SQL. Run. Yay! I got it right the first time. Right, so that's basically my nice little joined up track list. Oh, I'm so happy that I got that right the first time. Okay, well you can play with this yourself. Play with this tracks, maybe make an export of your own iTunes library and run it with that. And so I hope that you found this particular bit of code useful. Okay? Cheers. So our last major topic is called many-to-many relationships. And up till now, everything that we've done is what's called a one-to-many relationship. And that is, there are many tracks associated with one album. There are many albums associated with one artist. There are many tracks associated with one genre. And you can think of labeling, and as you look at data models, they put little labels on each arrow that tell you which end of the arrow is the many and which end of the arrow is the one. And so in this case, the foreign key is pointing to, there are many of these rows over here, many rows that point to one row over here. So it's a many-to-one relationship. There are various ways. Sometimes I'll put two arrows at this end and one arrow at that end. But whatever it is, this kind of thing we've been showing is a many-to-one relationship. And that's probably the most common thing. But there are times when you just can't model things with a one-to-many relationship. So like if you have a mother and children, well, that's a many-to-one relationship, and it's just fine, and that works fine. But sometimes you have a many-to-many relationship in that there might be many books. One book has many authors, and each author has many books. And so you don't have like the one side. There's no one. And so you have to end up building a table that what we call, I call it a connector table. They call it a junction table on Wikipedia. But we need a little table that allows us to break a many-to-many relationship into, in effect, two many-to-one relationships in a connector table. And so this is a connector table. So you could think of this as, you know, there are many links here, but we don't have a way to model the many over here to here. And so what you do is you basically say, oh, there's a lot of these things. There's many that go to the one, the many that go to the one, and then in here you sort of create that manyness that you want to create. So it's probably just as easy to look at a sample of this. So let's imagine a learning management system where you're taking a class, and there are some people that are teachers and some people that are students, and many students are members of many classes. A student can be part of many classes, and a class has many students in it. So you can't really find the one end. And so what we do is we make a table called membership. And in that table of membership, we actually often don't put a primary key in at all. We simply put in 2 foreign keys. And if we're going to put a uniqueness constraint, we put a combination of the 2 foreign keys as the uniqueness constraint. So we say there could be duplicate user